So thank you everyone for attending today's Foxconn Quantum Computing Seminar. Today we have the pleasure of having Yujie Zhang, who will tell us about all entangled states can be certified by a violation of non-contextual inequalities. So Yujie is a postdoc at IQC in the University of Waterloo. Also has an affiliation with Perimeter Institute. Yujie received his PhD from University of Illinois at Urbana-Champaign. His research lies at the intersection of photonic quantum information and quantum foundations, focusing on non-classical features of quantum mechanics through concepts from quantum foundations and applying this on the design of novel photonic quantum protocols. Yeah, so Yujie, the floor is yours.
Thank you so much. Thank you for the introduction and thank you for the invitation. So today I'm just going to give an introduction to our recent work. As I mentioned, like my research interest lies in the intersection of photonic quantum information and quantum foundation. So actually, this is actually quite representative about what I was interested in and what I was still doing right now. So as the title suggests, the talk will be mostly about trying to understand entangled states, but from probably two perspectives. One is like from a quantum foundational perspective, how one can actually redefine entangled states from a different operational meaning. And the other one is like how one can actually define or design novel tool for entanglement certification that is different, completely different from all existing tool and actually have some certain features that is not actually jointly met in any previous approach. So this work is a joint work with a bunch of theoretical collaborators from Perimeter Institute, including David Schmidt and Thomas General and Robert Speckens, and several experimentalists from IQC. So I will present a little bit of our experimental demonstration, but mainly the talk will be about the theoretical idea behind the experimental demonstration. So there are three references over here. The most relevant one is the last one. It's the one that I'm going to talk about, which is actually making the connection between the quantum foundational topics to the bipolar entanglement and how that can be used to derive new entanglement certification. And the other two references is also going to be very helpful if you find the topic interesting. So as I mentioned, the talk is going to be about an intersection between these three different subfields of quantum science. So from the quantum foundation part, the whole project that I'm going to present, actually it is motivated by a bigger project that we are trying to reassess what is classical in quantum theory. Like we want to make a definition and try to articulate why that definition is appearing and what kind of feature that definition has. And for people who are not in that field, you can refer this definition of classicality as Leibniz classicality, because a lot of underlying principle that we are trying to go with is based on Leibniz principle. And from the more quantum information theory side, an interesting feature about our new notion of classicality is that we realize the new notion of classicality is actually connect to a lot of different traditional notions of non-classicality. For example, we can show from our framework, we can rederive what do people usually define as entangled states, as steerable state, non-local states, entanglement non-protein channel, and a lot of other familiar notion of non-classicality that people are familiar with. It can all be redefined through our reassessments of classicality of individual quantum processing. And to the experimental side, like as a tool, as a consequence of our connection, we can show that we can develop new tools that can be used to certify entanglement. The certification is not exactly device independent, but I will show you and I will try to convince you that it is almost device independent. So it has a lot of good features. It doesn't require you to make a lot of assumptions, but it can allow you to characterize all entangled states. So to make that kind of argument slightly more specific, here I have a diagram over here try to show different entanglement certification approach. The x-axis over here is just representing how many assumptions you have to make in your certification approach, and the y-axis over here is about the detection power, like how many entangled states that you can actually detect using the corresponding certification methods. The most straightforward one for people who do experiments is actually just based on quantum state tomography. You just run a quantum state tomography, you get the density matrices, and then you decide whether the state is entangled or not. And obviously, you have to make a lot of assumptions. So this has the strongest assumption. You have to making sure you have a full characterization of the measurement devices so that you can trust your tomography results. But the detection power for this one is particularly good because in principle, you can certify all entangled states based on your tomography results. On the contrary, people also discuss a lot about the most the certification based on the weakest assumption, and that is known as the device independent test or Bell test. In this case, basically the only assumption that you have to make is the Bell causal structure that you have, essentially the local causality and the agent-free choice. But the downside for this approach is that the detection power is known to be not so good. And people actually know that there are a lot of states that is known to be non-local, meaning that they can violate some non-local Bell inequality. They are not actually, but that set of states is actually a strict subset of all entangled states, and actually it is arguably a very small subset of all entangled states. So over the past years, there are a lot of refined methods for entanglement certification that is sitting in between of these two external ones. For example, they are the so-called measurement device independent test. So instead of actually having characterized measurement devices, people can replace the classical input with a quantum input. So you only have to characterize your quantum inputs. You don't have to characterize your measurements. And the benefit is that you can, in fact, detect all entangled states by just using this measurement device independent approach. And similarly, people have also devised like a more complicated approach where you don't even have to assume a perfectly characterized quantum inputs, but instead you need to assume a more complicated causal structure. And you also have to make some assumption like source independence and extra. But the benefit is that you can, in principle, show that all entangled states can be certified using these methods. But even though these two make much less assumption than the tomography-based approach, they still make some assumption. Like they still make some assumption about what extra quantum system you actually have, or make some assumption about what extra causal structure that you actually have for the certification. So basically speaking, simply put, the new certification that I'm going to introduce in this talk is a new one that we arguably believe is making less assumption than all the previous one, but we can still certify all entangled states. So I'm going to discuss the assumption in a little more detail later, but simply put, just try to put that in the upfront. The two assumptions that we have to make, the first one is the same as the device independent approach, where you have to assume there is a Bell causal structure, meaning that we know the causal structure is of this form as the diagram over here described. And we also have to make some assumption about tomographic completeness. So this terminology sounds a little bit like distracting. It is not the same as tomography. We just need to making sure we know the magnet that we implement in the experiment is complete, in the sense that we can in principle get all the tomography results, but we don't have to run the tomography. So we don't actually need to characterize those devices. But I will make this clear. So this sounds a little bit weird, but this is actually the only two assumptions that we have to make. But the benefits for this test is that we can actually detect all entangled states using one specific test based on generalized noncontextuality or generalized contextuality. So far, any question? Okay. I will try to go with a detour. Like I'll get back to the certification methods in the end, but I want to give like a broad overview about how we get motivated and what kind of extra thing that we can do using the same framework. So let's start with two basic questions. The first question is, when is a set of statistics classically explainable? So this is about big definition. And the second question is, when is a single process classical? So we want to make these two questions clear before we can actually introduce the certification method that we are going to have based on this definition. So people actually have like historically, there are a lot of like well-motivated definition for classical explainable statistics. For example, in the bipartite Bell scenario, well, the quantum representation of a bipartite Bell scenario is as follows. And people know that the quantum theory tells us the distribution in this circuit will be predicted by quantum theory as follows. So we know the density matrices, we know the effects, then we can actually predict the statistics from the rule of quantum mechanics. And people usually articulate that this kind of quantum circuits, the Bell circuit, is classical if you can find a local hidden variable model, meaning that you can find a way to decompose your statistics based on some distribution describing quantum states and some distribution describing the response functions of the madness. So if you can do so, the common view people will say is that the quantum statistics in the bipartite scenario is classical if it admits a local invariant model. So that's the common view in the Bell scenario. There are also some common view in the prepared measure scenario, so which I call prepared measure circuits. Again, quantum theory tells you that there is a certain prediction about the quantum statistics. And the scenario is less well understood because if you just ask for an ontological representation, meaning that you want to reproduce your quantum circuits using an ontological representation where each individual quantum states are described by some distribution and each element is described by some response function, then you can always reproduce that in the ontological representation if you don't have any restriction. That's why people usually try to add some extra restriction in the ontological representation. For example, people can ask that maybe we shouldn't ask ourselves to have infinite cardinality of the hidden variable So you can make some dimensional bound on the hidden variable. And that's the so-called dimension weakness that people are building in the prepared measure scenario. But our approach is slightly different. We are trying to add a constraint that is coming from the principle of generalized noncontextuality. And that constraint essentially saying is as follows. If we have a set of states that satisfy a linear equation of this form, where alpha x over here are all just real number. If we have a set of states that satisfying this linear equation, we ask ourselves to reproduce the statistics in the ontological representation where all the ontological representation of the quantum states also satisfy the same linear equation. So we call this linear equation over here as operational equivalence relation in quantum theory. And all of this relation over here as ontological equivalence relation in the ontological representation. So essentially, this is asking us to find the linear map between the quantum circuits to the ontological circuits. And this is actually underlying the assumption of generalized noncontextuality. So maybe for many of you, you may heard about Cohen-Speck contextuality more compared to the generalized noncontextuality. There are a lot of historical debates between these two different notions. I'm not going to articulate, but for this talk, the only thing that you need to understand is that the principle of generalized noncontextuality tells you that if you have this equation hold on the physical level, then you should have the equation hold on the ontological level. That's the only thing that is implied by the generalized noncontextuality. So then the common view, so for more detail, you can always find in this paper, but the common view in the prepared measure scenario is as follows. The quantum statistics in the prepared measure scenario is classical if it admits a generalized non-contextual ontological model, which is defined by this decomposition and this restriction from the principle of generalized non-contextuality. So these are the two common views that people actually have studied a lot, but actually they can be combined. They can be combined in a way that on the left-hand side, when we say that we have a local invariant model, we are essentially saying that we ask for diagram preservation, meaning that if whatever the quantum circuit looks like, we want our ontological circuit looks like the same. And on the right-hand side, we essentially ask for linearity. So it means that whatever the quantum circuit is, whatever the operational equivalence or linear relation that we have on the quantum circuits, we want that to be preserved in the ontological circuits. If we combine these two, actually, that is the definition that people are using in the modern study of generalized noncontextuality, meaning that a quantum circuit is classical if it can be mapped to ontological representation, where the map is linear and diagram preserving. And from a category theoretical perspective, this is just asking the existence of a fine function that is mapping from the category generated by the quantum process to a suitable classical stochastic category. So I'm not going to explain any more detail why people motivated this definition, but for the rest of the talk, you just have to take this as the starting point of our discussion. We make a definition about what is classical, and the definition is motivated by the principle of generalized noncontextuality. And the definition has two ingredients. One is about diagram preservation, and the other one is about linearity. So the one benefit about this definition is as follows, is that it can actually be applied directly to all scenarios. If you can draw a quantum circuit, then you can find a way to define what do you mean by the quantum circuit to be classical. You just ask yourself to reproduce the prediction of the quantum circuit such that the reproduction, the map for the ontological representation satisfy the two principles like linearity and diagram preservation. So for more detail about how to treat this kind of classical experimental statistics, you can find that in one of our earlier paper. But I'm going to try to give one example of that. That is the bipartite scenario, the bipartite Bell scenario that we are going to discuss. So on the left-hand side over here, we have a quantum circuits, which consists of like quantum state and a few different quantum measurements. And if the quantum circuit can be mapped to an ontological circuit in a linear and diagram preserving manner, then we say that quantum circuit is classical. And what is essentially the constraint that we add over here when we are discussing classical? It has a few ingredients. So the quantum circuits originally we have predict a quantum statistics of the following. So the diagram preservation asks us to at first try to find a way to decompose the quantum statistics based on a diagram that consists of only stochastic representation. And the diagram should be the same as the bipartite Bell circuit. That's the diagram preservation. And if you are familiar with Bell inequality or local invariant model, this is essentially a local invariant model, but just we call that differently in this context. But linearity is a little bit more involved. There are a lot of different consequences about linearity. The easiest one that one can think of is that since there are only one quantum states, so there are no linearity that you should talk about by mapping rho to the joint distribution. There are just one single atom, so there are no equivalence linear relation that you have to talk about. But for magnets, for both of these two magnets, you can find a lot of different operational equivalence. So essentially some linear equation satisfied by those effects. And the linearity for the map just asks you to making sure when you reproduce the statistics using an ontological representation, they all satisfy the same operation at n. So for any alpha ax over here, just a set of real number, such that the operational equivalence holds, you ask yourself to have the equation also hold on the ontological level. So this is what you have for each individual single process. There are only 3 different individual processes. But the tricky part is that there are more compositional structure that you can have in the bipartite scenario. For example, you can do some composition between the state on magnet on one side and the bipartite state. That effectively gives you a steering state. Essentially, that is a proportion on both sides. So if you do magnet on either side, you get a proportion on both sides. The diagram preservation is not only on the level of individual process, you also ask the diagram preservation to satisfy on the compositional level. So the combination of these two should also be linear mapped to a combination of these two. Essentially, the combination about the ontological representation of the effect and the state should also be linearly mapped from the combination of the physical measurement and the physical bipartite states. So essentially, you need to define a little bit more operational equivalence, including the combination between n and p that gives you a bunch of extra linear equivalence among compositional process, and the combination between the measurement n and the proportion p also gives you some extra combination that is among the proportion on the eddy size. So you also ask yourself to respect this extra linear relation. So this is a little bit puzzling, but I just want to share the full detail. Most of them is not going to be appearing in the following talks. In the end, there are actually a last, slightly even more involved constraint that you can have. That is saying that these two processes give you a composition that defines a state that is propelled on eddy size. And these two processes define a steered state that is being propelled on the other side. So then we can talk about, though you only have one bipartite state, but you actually have a lot of different marginal state on both sides. Then you can talk about whether the representation that I have representing the bipartite state, that is P lambda 1 lambda 2, is actually also satisfying the corresponding linear relation that is resulted from all of those marginal states that we could have in the circuits. So all of these have to be considered together to amount to our definition of a classical experimental circuit. So it's a little bit complicated. I will give you a few results to try to persuade you that it's actually not impossible to characterize. But other than the first two constraints, it is true that all the last 3 constraints, they are not even linear constraints. They are non-linear constraints because you actually are defining some compositional structure, and the constraint is linear on the compositional structure so that they are non-linear on the level of individual representation. But don't be scary, it can still be characterized. So we just mentioned, like definition-wise, what do we mean by a circuit to be classical expandable based on the assumptions generalized on contextuality. Then how that could be helpful for us for entanglement certification. That's boiled down to the second important question. That is, what is a single process classical? Can we, based on the classical statistics, to induce a definition of a classical process? And the answer is yes. Well, I'm not going to explain that in detail, but you can find that in our first references. The theorem one in that reference is essentially, we show that in a rigorous way. We can make a good definition about when a process is classical, defining the so-called factorized due process of it. So for a bipartite state, the factorized due process of it is those product effects. And then essentially a bipartite state is classical if and only if for any arbitrary product magnet that you can think of in quantum theory. When that set of product magnets composed with your target bipartite state always admit a classical statistics, then your bipartite state is classical. So this kind of definition is quite similar to the definition essentially of non-local states. A non-local state is essentially defined in the sense that if a state cannot violate any value inequality, if a state always admits a local invariant model, then we say a state is non-local. So our definition is analogous to that, but slightly different. We are essentially saying that a state is classical, or we call Leibniz classical in our case, if and only if when the state is composing with any arbitrary product effects, we always get a classical expandable statistics based on our previous definition about classical expandable statistics. So this is the starting point that actually for the following discussion. Any questions so far?
I'm just curious, like, so when you're calling this Leibniz classical, I guess I need a reminder of what Leibniz principle is.
So the Leibniz principle is actually, so Robert Frackens had a paper about Leibniz principle, and the core idea is essentially as follows. So if you have a set of process, for example, if you're looking at the operational equivalence condition over here, if you have a set of process such that they are indistinguishable in the sense that they satisfy this operational recurrence condition. So the linear combination of them equals to the zero operator. That means that they are operationally indistinguishable. Then if you are looking for an ontological representation of that single process, they should also be ontologically indistinguishable. So the use of Leibniz principle in this context is essentially, if you have a physical theory such that the component of the physical theory is not distinguishable at all, then they should not be distinguishable on the ontological level. And that's essentially this linear relation over here. If we have a physical theory that satisfies this equation, then on the ontological level, they should also satisfy the same equation. So that's what I mean by Leibniz principle. So, but this is more from the quantum foundational side that people have articulated a lot. So it's not so important for the following discussion. That's why I try to avoid talking about too much detail about it.
And maybe my other question is just that, like, so, like you say that, like in this Bell scenario, that you also need to consider some linear conditions from the steering part, right? Where, but so what happens if you forget? Like, I actually don't impose those.
I will come to that exact point in a few slides.
Okay.
And actually, the highlights to connecting to entanglement is about forgetting some operational identity. I'll get to that point very quickly. Okay, so let's present some general results, not about entanglement certification yet, but almost there. So as I mentioned, like the definition, a good definition is analog to the definition of non-local state will be a bipartite state. Bipartite state is Leibniz classical if it generates statistics that are classical relative to all these operational identities. So if for all possible measurements that you can compose with the bipartite states, if the statistics is still classical such that you can respecting all the operational equivalence condition over here, then the bipartite state is classical. This sounds pretty, but actually it turns out that it has a very simple characterization. We can show in our, parallel paper, a bipartite state is classical based on this definition, if and only if it has a product frame representation. So a frame representation is essentially an over complete basis representation. And the product frame representation only have like a few constraints over here. the constraint includes that these two pair defines a frame, and these two pair on A, and these two pair defines a frame on B, and the sigma lambda 1, lambda 2 over here, lambda A, lambda B over here are positive and definite operator, like they are density matrices. And the coefficients over here are positive. So as you can already see from this theorem over here, bipolar state is particle. A necessary condition for it is that it has to be separable at first, because this kind of free representation is more stringent. It's a more stringent constraint than a separable state. It has to be separable at first, and it also has to satisfy some constraint coming from the product representation of product frame representation. So this is the general result that you can characterize. So though all of this operating identity looks scary, but actually it turns out that the corresponding non-classical or classical state that it induced is a very clear and very clean, has a very clear and very clean analytical representation. So, and this is what we have in the most general case. But actually, what is more interesting for our following discussion is not the most general case. As what was just asked, in the most general case, we have to consider all different operating identities, like these 5 operating identities. And actually, some of them is quite scary. But if we try to make a definition for classicality relative not to the whole set of operating identities, but actually a subset of operating identities, can we make a definition? Can we calculate the definition? And can that definition be interesting in any other concept? And the answer is yes. And there is a full table of that. We can try to, so there are 5 different operating identities that you can have in this scenario. You can try to discuss some of them or all of them or a subset of them. And the interesting part is like, if you don't consider any of them, you get local state. That's obvious, because if you don't consider any of them, then essentially what you have is just a local invariant model. So you get local states. If you consider just ON, that's the operating identity described by the measurement on the edge size. Then you can show that the state that is practical in that sense is those unstable states from B to A. And similarly, you can define those unstable states from A to B, unstable state on 2 sides. You can also define separable states. And this is our focus for the talk. I'm not going to talk about all the other, but that's the highlight. You can actually connect into all the other, but you don't have to. You can try to pick up the right operating identity to discuss the right object that you're interested in. And there are actually another 4 different ones. That is the scary part. You take the other operating identity that is actually nonlinear. That gives you something that is a little bit scary, but it is doable. You can still show that they are corresponding to some other well-formulated definition of classical states that is not known before, that is in our parallel paper. And another feature that I want to mention is a conjecture yet, it's not a full theory, is that for a d by d dimensional system, so I have to restricting myself to having the same dimensional hero space on both sides of a bipartite state. You can show that in that scenario, we have a conjecture showing that all of these 4 are actually measure 0, meaning that the classical states that is separable, the non-classical state that is separable is actually measure 0. So essentially, most of the non-classical states are the entangled state. They're only a measure 0 portion of non-classical separable state that you can basically ignore. But you can construct them on purpose, but in real life, you just never met them. So that's our conjecture. It's not proof, but we have a lot of evidence to show that we actually don't have to worry about too much. So this diagram over here is a little bit misleading because, as I mentioned, the classical state that we conject is actually almost overlapped with the separable state. It's measure 0. It's a little bit different, but basically measure 0. Okay, so the rest of the talk will be about how we are going to utilize the fact that the classical relative to this operating identity gives a separable state. That's the starting point that we are going to have to develop the certification methods. And actually, the idea is quite simple. So for people who are familiar with Bell inequality and local invariable theory, people know that if you try to get a Bell inequality, then essentially the step that you need to have is try to build a local polytope. You just try to describe all different distributions that is compatible with local invariant model, and you get those boundaries, and those boundaries are Bell inequality. And the story about how to get non-contextual inequality is essentially the same. Assuming that we don't have the set of all measurements, we just have a subset of measurements. We know that this is sufficient for us to get a if we get a violation, we have a sufficient condition for entanglement. It's not necessary because in order to get that to be necessary, we have to have all measurements. But if we only have a subset of measurements, we can still get some kind of sufficient criteria for entanglement. So if we only consider a subset of measurements, like the Bell scenario, we can always consider a scenario that you only have a few settings. Then you can actually try to build the local non-contextual portal. So that's a generalization of local portal. The portal is built by this decomposition, the local invariant mode decomposition, and a few linear constraints. So this linear constraint will only be cutting the local portal. So originally you have a local portal being a really huge dimensional probability space. But if you have a lot of different non-contextuality constraints, you are essentially cutting constraint on the local portal, and you are looking at the non-contextual portal that is in a smaller dimension. But the non-contextual portal is guaranteed to still be a convex portal. So you can actually use almost all the tools that you have in analyzing Bell scenario to get the inequality for the non-contextual scenario. There are some caveats. For example, there are some irrational numbers that will going to appear in this scenario, but those are not the main issue. That you can still go around that by calculating them. So the essential story is for the Bell inequality, we get that from local portal. And for our case, we want to use the non-contextual portal to help us to bound the set of entangled state. Then we just get a different portal, and we just calculate those portals differently, and we get new inequality, which we call non-contextual inequality. And I'm going to give you a few examples to show you how powerful it is. So in order to do that, I just want to have some like test example. And the standard one that people typically use in studying entanglement nonlocality is a family of isotropic states, a qubit isotropic state, for example. For this state, people know the state is non-local is known to be non-local for value greater than around 0.69, defined by the Grothendieck constants, which is a constant that people don't really know the process value. And people also know that the state is steerable if it is above 1/2, and the state is entangled if it is above 1/3. So the first example that we can have, we call that square scenario, but essentially it's essentially a two-setting, two-outcome Bell scenario. So you only have two inputs on both X and Bob, and you have two outcomes. Both of those two measurements are binary outcome measurements. The interesting feature for this example is that in this case, you can show all of these operating identities are the same, are trivial operating identity, because the only operating identity that you have is a normalization condition. If you only have two binary outcome measurements, the only linear relation that you have among those effects are normalization condition. The normalization condition is automatically satisfied by the normalization condition of the reasonable function. So you don't actually get anything. You actually, what you actually get in this case is that all these portal, non-contextual portal and local portal, they coincide. So this is the boring case. You don't get anything. And the only inequality that in this case you have is Bell inequality. And the only certification that you can have is for p greater than 1 over square root of 2. So that's what you can get. But if you start to adding more measurement settings, for example, in the what's so-called octahedron and cube scenario, we have 3 binary outcome measurement on the one side, satisfy geometrically this kind of operational equivalence condition, meaning that like these two added up together equals to these two and equals to these two. So that's all the operating identity that you can have on the left-hand side. On the right-hand side, you have more. Like you have the anti-parallel pair added up together to be the same. You also have the fact that this tetrahedron, like this tetrahedron built by this 4 point, they added up together equals to the other tetrahedron built by the other 4 point. So that's not implied by normalization condition. And then you can show that actually you also have you start to have some inequivalence between some non-contextual portal. Some of them are still the same, but you still start to have some inequivalence. And you can actually show, you can fully characterize the non-contextual portal, and we can get a lot of inequality. That is a non-contextual inequality, not Bell inequality anymore, because we get more constraint in this case. And you can show 2 things. The first thing is that this inequality is also a steering witness, because as I mentioned, like this non-contextual portal actually coincides with the non-contextual portal that is useful for characterizing quantum theory. And the second point is actually more interesting point is like you can show for the first inequality in the table over here, you can already use that to certify entanglement for p greater than 0.57. That is actually much better than all Bell inequality already. So the best Bell inequality people actually know is actually on the right of this boundary. So people only know how to certify entanglement using Bell inequality up to 0.7. But this simple example 2 already allow you to certify much more isotropic states than the standard Bell inequality. You can actually do more. I'm not going to elaborate them, but you can actually do more. You can actually consider the so-called exohedron and decahedron. So there's some reason that I'm choosing this symmetric one, but you don't have to. I'm choosing this symmetric one because that allows me to get a quite analytical expression of the boundary inequality. But you can already see that there are some irrational number already. This is already more complicated than the previous case, but it is quite symmetric, so I can still get some inequality. But the highlight for this new inequality, this is actually what we run experimentally. The highlight for this new inequality is that you can actually show for every p greater than around 0.41, you can get a violation of this inequality, meaning that for any isotropic states with p greater than this value, you can certify them to be entangled using this approach. So that's actually much better than all Bell inequality and also all steering inequality for device independent test. And you can actually do more. Like you can do more numerically. You can show that I can define some geodesic and Goldberg polyhedron that is like a more complicated polyhedron with a lot of vertices. You can actually show by increasing the level of the division of the polyhedron, you can actually get the value closer and closer to p. And actually you don't have to use a lot of methods. You can get the value to p quite easily. So just this is the proof of principle numerical demonstration showing that yes, it's true. You can certify at least for the family of two-qubit isotropic states. You can certify all entangled isotropic states using this family of non-contextual inequality. But that's not the most convincing argument because there are a lot of other states, a lot of other two-qubit states. What if this only works for some symmetric case? And that's apparently not the. Oh, sorry. Before that, okay. People may confuse that I mentioned a lot of symmetric examples like exohedron, cube, octohedron, but those are not necessary as I just mentioned. And this example 5 over here is trying to convince you that is not important. This example 5 over here is done by constructing randomized methods. So meaning that we don't actually have to define a very symmetric method strategy. We just randomly pick some projected methods and then try to get operational recurrence condition for whatever those randomized measurement has. And then we run the corresponding non-contextuality test. And for this table over here, I draw 100 independent trials for each different m, meaning that I choose m binary measurement on S and m binary measurement on Bob. And you can show actually just randomized measurement. You can get a certification quite well below the threshold that you can do using Bell inequality or using steering inequality or using any other approach. And another highlight for this randomized measurement is that you don't have to worry about experimental imperfection. You just do arbitrary measurement that you can have, making sure that they are like close to projected measurements. That's something that maybe you definitely want. But other than that, you don't have to calibrate your devices to making sure that they are quite symmetric. You just run that randomly, and then you extract the data, and then you run the test, and then the test result can help you to get a sufficient condition for whether the state is entangled or not. And actually, the performance of them is actually pretty good. So this is the fifth example. Get back to the point that I mentioned that all of these examples only works for two-qubit isotropic state, but this is not the limitation of our approach. We can actually run a different numerical check to show what percentage of randomly picked two-qubit entangled state can be certified by different methods. So as the comparison over here, I choose the CHSS test with a fixed basis as an example, and also a CHSS test with an optimized basis. So meaning that for one, I just pick one two outcome measurement, arbitrary one, and try to certify the percentage of them that is being validated by that single strategy. And for the second one, actually for each individual sample, I also optimize the measurement basis. Actually, you don't have to do that in practice. You can just use the hierarchical criterion to tell the optimized basis result. But the highlight is that even if you optimize basis in the CHSS test, only 1% of entangled states that is randomly sampled using like a Hermitian using a Hilbert-Schmidt measure to randomly sample that only 1% of entangled state can actually be shown to be non-local or entangled using the Bell inequality. But using our approach, even just a fixed set of measurement strategy, you can certify more than 3/4 of entangled states using one single test. So what that tells you is that in experiment, if you have a state that is not showing entangled or not, you just run one specific test. If you get a violation, then that's a sufficient criterion telling you that the state is entangled. And actually, more than 75% of the entangled state can be certified by using that one single approach. So this is the final example that I'm going to show. Any questions so far? I will ask. Any question up to here?
Okay, I think I just wanted to ask, like, so when, let's say when you were considering the random measurements, isotropic states, so I guess there is a systematic way to find the operational equivalences that you need.
Yep, I will mention that. Yeah, actually, it is in one of the last slides. Yeah.
Okay, okay.
The operational recurrence, there are two ways to do that. One is that you assume operational recurrence. Once you get the statistics that doesn't satisfy that operational recurrence, then you can enforce doing some critical processing to get the desired operational recurrence that you impose. That's the first approach. And there is a second approach. You don't have to assume operational recurrence. You just learn the operational recurrence from your data, which is something that I will try to describe in this slide. But that's something that you can learn. That's always something free to learn from external data that is not learned before in a standard Bayes test. So arguably, you can say that in the standard Bayes test, people don't use all the information in the data. People just use some of the information to derive the inequality. But actually, it takes more. You can use more data from the standard Bayes test that you previously ignore. And actually, those more information allow you to certify much more entangled state and eventually all entangled states.
Yeah, because I understand that, yeah, when you choose the symmetric measurements, of course, in some sense, those are chosen, the symmetrists help you to find the nice operational equivalences.
Yeah, the symmetry allows you to get something nicer so that you can get something analytical, but it is never required in practice. In practice, you can just ignore those nice looking inequality, but just run an ugly looking inequality, but you can still certify entanglement in the same way. So, okay, let me try to articulate, hopefully in 10 minutes, how to test this experimentally, because there are still sounds like some assumption that I'm making, and I want to make sure that assumption is understandable and arguably much weaker than the assumption that people have to have in other device dependent scenario. So this is definitely more assumption than device independent scenario, but I want to argue that it is not too much more. So this is a brief justification as follows. Sorry about the animation. On the left-hand side, in the Bayes test, the assumption that people usually have is essentially the Bayes causal structure. So the local causality and the agent free choice, they're all about Bayes causal structure, which typically is guaranteed by your belief in special relativity and your belief in your clock and ruler, because you need to measure the space-like separation based on your clock and ruler before you can trust your space-like separation. So, and the space-like separation in the Bayes test implies that you have in your operational data always satisfying this non-signaling relation, like summing over A is independent of what you have as an output and input of B and Y. So that's the non-signaling relation that is guaranteed by the space-like separation. The noncontextuality test is slightly more stringent. It makes a little bit more assumption. It also makes the assumption about the Bayes causal structure, similarly to the Bayes test, but it also makes the assumption about the operational equivalence among all of these measurements. That's what we were talking about earlier. The way to understand where is this operational recurrence and how we can see that is as follows. If we assume that we have some operational recurrence among the effects on the eddy size on the measurement N, then we definitely know this implies that when we're looking at the data that we got experimentally, the PAD given XY, they must satisfy the same operational recurrence as that's satisfied by the physical process, meaning that the operational recurrence on the physical process, they already imply the operational recurrence on the ontological process. So some features about the measurements is encoded in the statistics that we observe. And the only thing that we need to do, the only assumption that we need to make our test doable is do the reverse. Like we need to make an assumption so that we can get the operational identity on the physical process from the data that we actually observe. And the assumption is what we call tomographic completeness. And specifically, it has like two ingredients. The first ingredient is like we look at our data table, PAD given XY, and we're looking at features such as the the data table always satisfies this particular linear relation. It must be if you have a lot of different measurements, because I already told you that if you have a lot of measurements like that, they have some linear relation, then there must be some features in your data table that satisfy the same linear relation. And conversely, if you have those data satisfy the same linear relation, then if you also assume tomographic completeness, meaning that your measurement is already tomographically complete, meaning that the measurement already tells you all the information about the statistics, then you can, based on what you get from the statistics, the operational recurrence in the statistics, to backwardly engineering out what is the operational that you really have on the physical level. And that is the ON and ON that I used in the previous example. And then the step using this approach will be randomly making measurement on your bipartite states, get your data table, try to infer the operational identity from the data table, using the operational identity that you get from the data table to construct non-contextual inequality, and then testing your data table with that non-contextual inequality. If you get a violation, you get a sufficient criterion for entanglement for your bipartite states. So that would be the key steps. So if that's not convincing enough, there is a second justification about operational identity. It is as follows. So as I mentioned, the standard quantum state tomography, that makes the most assumption because it requires the full characterization of measurements. And the benefit is that you get a unique solution of your tomography results. But if you run a test based on that tomography results, that is completely device dependent. There is a quite closely related tomography to state tomography. That is the so-called self-consistent tomography, meaning that you don't make any assumption about both your measurement and your states. But what you do is like you run a linear, you run optimization. You get a non-unique solution, which is a tuple, n and m and rho, that can realize your PAB gamma xy. The downside about the benefit about this approach is that you don't make any assumption. You still don't have to characterize your measurement and states. But the downside is that the solution is not unique. You will get a lot of different solutions about what your quantum state is, so that you cannot directly using this as a test for entanglement. You have to optimizing over all possible solution of rho. That's not going to be possible. But there's something that you can actually already extract from the self-consistent tomography, because all these non-unique solutions, they are related by some invertible map. So they are always be, if you have something that is going to realize the data table, then all the other tomography results that can reproduce the same data table are related by some invertible map. There are two key features about this invertible map. The first one is that there are two features over here. The first one is that operational identity, when we are talking about that, like those are essentially the linear relation among n and the linear relation among m, they are gauge independent, meaning that whatever invertible map that you have, people call that gauge, you always get the same linear relation among n and m. So even in the self-consistent tomography, though you can have a lot of non-unique solution, you don't have to worry about the operational identity to be different. They are always the same. And operational identity is the only thing that we need to construct our non-contextuality test. So that our non-contextual test is something that is going to be fit perfectly with the standard technology of self-consistent tomography. And this self-consistent tomography is different from the state tomography in the sense that we never assume the measurement devices. We never assume any characterization. We can just get that for free. So that's the second justification about how we can actually do this experimentally rigorously. So, okay, so one slide. This the paper is a experimental paper, but I try to ignore a lot of like detailed experimental setup and actually data analysis, but just want to show you the results. We take the inequality that we have. This is the inequality that we have 6 measurements on one side and 10 measurements on the other side. As an example, we can show that in our experiments, for all the state that is above, with p above 0.4 for 3 or for 4 around, we can actually use them to violate this inequality. So it is slightly deviated from the theoretical prediction because of the noise that we can actually characterize experimentally. But still, using these simple methods, using this single inequality, we can already outperform all Bell inequality and all steering inequality. And those are actually lying the boundary about one half for steering inequality, and the boundary that is around 0.7 for the Bell inequality. And in principle, one can do this experiment with much more settings. And actually, if you are not running that on a photonic setup, which is quite limited by the total integration time that you can have, if you are running that in some other superconducting qubit system, actually you can in principle do something that is much better and much more robust to noise. Okay, let me end over here with like a brief summary about the talk. And actually, this is the same slide as my first slide. So the whole framework that is not discussed today is actually hidden in the first referencing that I shared earlier. That is about a general framework to discuss criticality of a single quantum process. The bipartite state that I'm introducing in detail in this talk is just a special case. Actually, you can do that for any arbitrary process that you want. The second highlight for the framework is that it is not defining something that is like fancy and but not connecting to any standard notion. Actually, it is well connected to all different standard notions that people are familiar with: entangled state, steerable state, nonlocal state, entanglement channel, and a lot of other concepts can be really derived from the same from the same real assessments. You're just looking at different operating identity that gives you different quantity coming out. And the last highlight for this result is it actually gives us something that is practically useful. The new practical entanglement certification tool that hopefully I have convinced you that is, though not device independent, but it is almost device independent. I have a table here. I'm not going to introduce that in detail, but this is the table. Try to compare all different entanglement certification methods. And our method is the last one, and it is the first one that satisfies the first 4 different criteria that is never jointly met in the past in any entanglement certification methods. Yep, that's the last slide. I have some backup slides, but if it is related to the question, I will show that. But this is the last slide.
All right. So thank you very much for quite an illuminating talk. Yeah, I think we have maybe a couple of minutes for some questions, comments, or if anyone questions, you can unmute yourself. Ask it. All right, so maybe I'll go first. So yeah, like in the second point that you're making here. So for example, I could do something similar if I wanted to say something about like states, like magic states, like stabilizer and non-stabilizer things.
Yes. So the stabilizer theory can also be discussed in this framework with some modification. There's some caveat for two-bit stabilizer subtheory. That's actually the most difficult part. You won't be able to get the exact characterization of non-stabilizerness. But for Q-trait, for all-dimensional stabilizer theory, you can actually get a necessary and sufficient criteria to certify all non-stabilizer state or non-stabilized measurements. But for qubit, there's some caveat, but it's still doable. It might not be necessary and sufficient, but we can still derive some useful criteria for qubit stabilizer theory. Yeah.
Is it easy to understand why it's
the reason is the qubit stabilizer theory itself is contextual. Theory itself is contextual. Okay. Yeah, but for all dimensional stabilizer theory, they are non-contextual. So if you want to get certify some non-stabilizedness, you are going to try to certify based on the boundary between non-contextual and contextual. But if your stabilizer subtheory already in the qubit case is already contextual, then there's some caveat. You won't be able to get yourself a perfect certification. I mean, at least not in a trivial way, but it's still going to it is still possible to give you some either necessary or sufficient criterion for non-stabilizedness or magic. But it's much more natural to generalize that to those all-dimensional stabilizer subtheory because people know that those are non-contextual. And yeah, yes, 1 second. Yeah, so Yeah, just let me just try to show this slide. This is something that I didn't share today. This slide, I'm trying to persuade you that this also works for any arbitrary cases, and that's actually the case we discussed in the first paper. The general framework is useful, is interesting because we don't have to restrict ourselves to any specific process. We define a process by something that has quantum input and quantum output, classical setting and classical outcome. But all these process, all these familiar term people have in quantum information science, they are just process. And you can use our definition to define when they are classical and when they are non-classical. And then you can also show that the standard definition of classical or non-classical are just related to them. And actually they are the same in some special case. So that is the same link that you can have between entangled state and the classical state, that classical bipartite state we define. But you can make that same arguments for all different cases. And then you can actually derive a bunch of different statistical methods for all of those unknown process. Essentially for entangled breaking channel, people don't have a lot of tool to certify when a channel is entangled breaking. And actually, people usually may have to do actually attach that to some maximum entangled states, for example, to do that. But that's a lot of assumption. But if you run that using our class, you can basically attach some incorporation and attach some measurements, and then run a non-contextual inequality in the perpetual and measure scenario. But that's all of it. You can derive the same linear inequality based on the new scenario, and those violations will help you to certify as a necessary condition, as a sufficient condition for the entanglement non-breakingness. For the probability of entanglement non-breaking of a channel. So a lot of like good features haven't been fully explored, but it will be quite analog to what I just mentioned. Yeah, for the bipartite case.
Yeah, maybe just one quick question. So because I'm always thinking bipartite case. So of course you can also do multi-partite case.
Yeah.
And there's no like additional subtleties.
Yeah, there are no for the generalization to multi-partite case is straightforward. The subtlety may comes. Let me try to mention one thing very quickly. So over here, I have a characterization for what is particle in the bipartite case. And we have some conjecture, saying that the last operating identity over here is actually trivial for the bipartite case. And we definitely know it's not going to be trivial in the tripartite case. So there's something new happened on the level of classical multi-partite states, but it's not happening when we are just trying to study entanglement. If we are just trying to study multi-partite entanglements, it's the same story. Since we only consider the first two operating identities, you just having several more operating identities for different measurements. But if you are trying to study our notion of classical multi-partite states, there's some caveat. You can still have the project representation, but there's some maybe new features that only appears in the multi-partite case, but no, in the final level, not on the level of entanglement and separability. Yeah.